Good morning, and first apologies for the aspect ratio of my slides, and second thank you to the committee for considering me for this invited talk slot. So today I'm going to be talking about the perceptual and cerebral representation of natural sounds. Every day outside the laboratory, we are exposed to a large range of natural sounds that include voices, at times music sound, but also include many diverse sounds such as the wind blowing, frog croaking, and so on and so forth. So the task of our auditory system is to use the input acoustic signal to derive a knowledge of the acoustic environment and of the relevant portion of the acoustic environment, which is the sound sources that generate the sounds. Why is natural sounds research important? Well, first, in the healthcare domain, it can help restoring environmental awareness in individuals with hearing deficits. We have industrial applications in the AI revolution era, such as automatic audio captioning. But more importantly, for the auditory neurosciences, natural sounds at large are a powerful instrument for revealing the signal processing in the brain, given their high acoustic heterogeneity. And they can promise to produce scientific knowledge that is useful for creating generalizable theories of the auditory system. So today I will give a couple of relevant concepts, theoretical concepts from the psychophysics of sound sources, which is my starting field of research. Then I will talk about, briefly describe two studies that were meant to test the limits of an acoustic processing model for perception and fMRI responses. Then I will describe a more recent study on an extensive comparison of computational models of perception and cerebral responses. And finally, I will dedicate a good chunk of this talk to describe ongoing work that is meant to, whose goal is essentially to understand the nature and to model the semantics, the meaning of natural sounds. So when I was an undergrad student, I was very interested in the problem of timbre perception. What is timbre? According to the ANSI standard, timbre is that attribute of auditory sensation that makes it possible for us to differentiate between two sounds that have the same pitch, loudness, duration, spatial location, and so on and so forth. So timbre is a multidimensional attribute of auditory sensation that, as Al Bregman used to say, is defined in terms of a wastebasket category. Timbre is what we don't know of auditory sensation. And this was the research on timbre was particularly intriguing to me. And one of the readings that was very influential for my years of research to come was a chapter by Stephen Handel on the dual nature of timbre perception. What Stephen Handel emphasized in this chapter was that timbre can be conceived not only as a multidimensional attribute of auditory sensation, but it can conceive in terms of the recognition of sound sources in the environment, of the mechanisms of objects and actions that produce a sound. And this was backed up by a whole range of studies, even very old studies, on the identification and perceived dissimilarity of musical timbre, which showed that listeners separate very well between musical instruments that produce sound using vastly different mechanical systems, such as a string instrument versus a wind instrument. And the chapter of Stephen Handel brought to my attention the relevance of investigating sound sources every day. And at the time, another influential reading was the taxonomy of everyday sounds by Gaver, which it's a beautiful system that essentially organizes all the non-vocal sound sources that we might hear every day based on the mechanisms of sound production. And this is probably the most notable contribution that we have within the field of ecological psychoacoustics, which is meant to investigate, again, the perception of the sound source. And I embarked then in quite a long journey during my PhD, where I investigated the ability of listener to identify or estimate the properties of the materials of sound-generating objects. Is this glass? Is this metal, wood, and so on and so forth? So one of the lessons that I drew from this research was that provided that the characterizations are extensive enough, acoustic features, but also measures of the mechanisms of sound production, how fast do we strike an object, how elastic is the material, explain equally well the perceptions of listeners. So I was like, okay, is acoustics this powerful? What are the limits of a processing model that relies exclusively on acoustics? And this question was what led me to carry out two studies, one on the perceived dissimilarity of natural sounds and another on the fMRI responses to natural sounds. And in the first study, what I did was to contrast acoustic representations versus semantic representations. And in the second fMRI studies, instead, I contrasted the representation of sound features with the representation of categories. And to make a long story short, there was a message coming from these two studies that is, well, in general, of course, acoustics can explain our perceptions and our cerebral responses to natural sounds, but for a particular class of sounds, that is living sounds, and the definition of a living sound is a sound generated by the vibration of an object that is part of a living being. So this is a living sound, my voice is a living sound, but this is not a living sound, just to be. And so with this particular category of sounds, there was a weaker link with acoustics. For example, when we are asked to evaluate the perceived dissimilarity of living sounds, we tend to give responses that are more similar to how we evaluate the perceived dissimilarity of short text, short sentences that identify the sound source. Okay. And there are caveats to this research when we compare acoustic representations with, let's say, higher level semantic representations. The answer depends on how extensive our acoustic characterization is, obviously. And fast forward in time, we started with Elia Formisano a collaboration to understand through computational models how the acoustic input is transformed into representations of the semantics of the everyday sounds. And one of the outputs of our collaboration was indeed meant to use computational models to characterize such transformation. And this time, I was much more satisfied with, for example, how would you say, the comprehensiveness of the acoustic characterization that we considered. And here we consider three classes of computational models. First, we consider acoustic models, so we consider the cochleogram, the auditory image model by Roy Patterson, the modulation transfer function, a spatiotemporal modulation representation, texture statistics, and auditory dimensions, time varying pitch, brightness, loudness, and so on and so forth. A second class of model that we consider was semantic models, which are derived from verbal sound descriptors. We consider first the categories model, and then we consider natural language processing embeddings, such as word-to-vector embeddings. that map, let's say, the meaning of a word onto a higher dimensional vectorial representation. Finally, we consider sound-to-event deep neural networks, or convolutional neural networks in this case, which are in themselves a computational model of the auditory to semantic transformation. And we consider the network by Eshel, VGGish, and YAMNet. So we map these models onto two different data sets. First, the behavioral data set that I already described in my acoustic in the previous slides, where participants were asked to estimate the perceived dissimilarity of natural sounds, and then a 70 fMRI data set that was collected by Santoro and Formisano in 2017. And for both data sets, participants were exposed to widely diverse and heterogeneous natural sounds. So which among acoustic models, semantic models, or DNM models best explained perception and cerebral responses? Well, the answer is let's say, summarized in this slide. So here what I'm showing is for the different models. I'm showing, and for the brain, I'm showing a multidimensional scaling representation where each of the sounds is represented by a dot. And in each of these representations, the closer the sounds are, the more similar they are within either the computational models or in the brain. And here I'm showing the multidimensional space for Eshel gyrus, our proxy, let's say, for the primary auditory cortex, and in the posterior superior temporal gyrus. Just to say it here, we had very similar results in all the STG ROIs that we consider. Then again, try to get a visual idea of which of these computational models looks more similar to, for example, representations in STG. And the answer is that these representations are better approximated by what happens by the representation within convolutional neural networks. This is we found the same result with the perceived sound dissimilarity, where DNNs were the winning model, and we will come back to this later. But we had a unique portion of the variance of perceived dissimilarity that was predicted uniquely by the semantic models, including word-to vector, that we consider, and that could not be predicted by DNNs or by acoustic models. And in the winning models was also DNNs in STG. And here the quality of the prediction was so good that we essentially could predict all the non-noise variance that there was to predict, because we were essentially at noise ceiling. Then we asked which portions of the neural network best predict perceived dissimilarity. Perceived dissimilarity or cerebral representations in Eshel gyrus or in STG. And here what I'm showing is the predictivity of the different layers of our winning network, YAMNet. And we go from the initial layers, layer 1, which is the closest to the acoustic input, to the final layers, layer 14, which is the closest to the semantic output. And in all of these cases, you can clearly see that the winning layer, the most predictive layer, is intermediate between the acoustic input and the semantic output. Most of the research that we are now carrying out within this collaboration has been focusing on defining what the semantic of natural sounds is exactly. And the first step that we took to this purpose was to analyze the linguistic descriptors of natural sounds that we can find in already published taxonomies of natural sounds coming from many different fields: auditory cognition, soundscape taxonomies, and so on and so forth. And one quite obvious result, quite clear result that we got here was that when describing natural sounds, people focus on linguistic descriptors that refer to the sound source. And in particular here we took one step further. We tried to systematize these descriptors. We came up with quite some obvious categories, but it's good to have them written somewhere. And so what we saw was that the sort of linguistic descriptors that we use for the sound source describe either the what, which sound, what object generated the sound, such as shoes, the how, the actions that are used to generate the sound, such as walking, who generated the sound, the agent, such as a person, where the sound was generated, like the spatial context, such as nearby, and when the sound was generated, such as the temporal context, such as at night. Another step that we took to redefine and to have a better understanding of the semantics of natural sounds was taken by Michele Esposito in a recent paper. What Michele did here was to train convolutional neural networks to learn not sound event categories, but word-to-vector embeddings. And then what we did was to compare the ability of these semantic networks, MDNN networks that learn word-to-vector embeddings, to the ability of alternative networks or of semantic models, NLP models themselves, to predict perceived dissimilarity. And what we found here was that SEMDNN, again learning word-to-vector embeddings, outperformed even YAMNet, our winning model in the previous analysis, at predicting the perceived dissimilarity of natural sounds. And there is another aspect here that is worth emphasizing. So the perceived dissimilarity predictivity of this network was much higher than the perceived dissimilarity predictivity of word-to-vector itself. Why is it so? Well, because word-to-vector has been trained on a database of Google News that includes a lot of materials a lot of things that cannot be recovered from sound. For example, it includes, description of cats, recipes, cooking recipes, or politics pieces. And whereas when we learn these embeddings from sound, what we are likely doing, we are filtering out from the learning process all that information that is not specified in sound. So no cats, not politics, and so on. Another step that Elia took to model, to come up with novel models of auditory semantics, which Maria Araujo Vittoria mapped onto fMRI responses, was to create a novel ontology. An ontology is a more complicated taxonomy. It's a system for organizing, let's say, objects, in this case, verbal labels from sound. And this ontology includes two different branches. The first branch specifies the mechanisms of sound production, the actions, and it's essentially an augmented Gabor taxonomy. The second branch of this ontology instead focuses on who or what generated the sound, and is essentially a refined word net. And what we are starting to see now is that whereas YAMNet, in the blue bars here, whereas YAMNet is the strongest, the most predictive, the most predictive model for STG representations, in IFG, YAMNet becomes less relevant, and this ontology seems to be equally well predictive of natural sound representations in the inferior frontal gyrus. Another step that we took to come up with novel models of sound semantics focuses on the concept of word co-occurrences. And this is related to quite an old concept in the field of natural language processing, according to which two words have a similar meaning if they tend to co-occur frequently in paragraphs or sentences within a large corpus of text. And what we did then was to measure the co-occurrences of natural sound descriptors within a large database of verbal descriptions of sound scenes, the ODO-ACD database, which includes 1.5 million descriptions. And we use these co-occurrences to derive some statistics. And then we are starting to map this onto the dynamic cerebral response to natural sounds here below. And what we are starting to see is, for example, that the co-occurrence model, this is the predictivity of word-to-vector and of the co-occurrence model as a function of time from onset. What we are starting to see is, for example, that the co-occurrence model is more predictive than the word-to-vector model at a rather late latency, starting from around 750 milliseconds from sound onset. So, in this study that we are carrying out with Marie Plegat, Giorgio Marinarotto, and Christian Ferreira, we instead somehow try to bring most of this together by extending the modeling framework that we used for the analysis of behavior and fMRI responses to MEG responses, to the dynamics of natural sound representation. And here we consider 2-second long sounds and several sets of natural sounds. And more importantly, we consider again 3 classes of computational models: acoustic models, cochleogram, MTF, and auditory dimensions; semantic models, word-to-vector and the co-occurrence model; and then convolutional neural networks trained by Michele Esposito. And here we focus on these 2 networks because they have the same architecture, they have the same training regimen, and they just differ in the loss function, where the SEM-DNN learns word-to-vector embeddings, and KDNN instead learns sound event categories. Okay. And just to give some methods, here we use the representational similarity analysis. We brought some updates, and I would like to bring one to your attention, which works very well in particularly low SNR conditions. And this is the whitening, the theoretical whitening that published by Jorn Diedrichsen a couple of years ago. So when we consider distances between cerebral responses or to different sounds, or between model representation for different sounds, we have to realize that the distance between sound A and sound B is not independent of the distance between sound A and sound C. And so what Jorn Diedrichsen did was to come up with a method for removing the statistical associations from the distances that actually obfuscate the representation of models and boost model representation statistics, particularly again at low SNR. Let's check some results. Here I'm showing the time-varying predictive R-square on the left panels for the sensor level, and on the right panels in source space for a couple of areas. And in the top line, we are comparing acoustic, semantic, and DNN representations. And here we see again that DNNs are the best model, if not for a late latency window. And more importantly, in the bottom row, what we are doing is we are comparing the different components of this category learning DNN with the continuous semantic learning DNN. And what we see is that whereas the early layers of the 2 networks are very, and which are quite similar, are very predictive of the initial, let's say, onset-related response, in this case it's 250 milliseconds. at around 500 milliseconds, from 500 to 750 milliseconds, what we have is a predictive dominance of the late layers of this of the semantic DNN network that learns a continuous semantics. And from our ongoing source level analysis, we are starting to see that this dominance might be coming from the auditory system, Eschel-Jarus and STG in the left hemisphere. I would like to finally mention the work by Cristian Ferreira on the temporal interaction of dynamic model representation, where we extend the temporal generalization method with partial information decomposition to measure two distinct ways in which representations in the brain at different latencies can specify a given model. So we have redundancy, which measures overlapping model representation, and synergy, which actually measures complementary model representations. And please check out the poster of Christian. And I would like to conclude with a mention of our next steps, which will be to extend our modeling framework to natural sound scenes. And please reach out if you're interested in this line of research. Thank you.
Thank you very much for this wonderful talk. We have time for a couple of short questions. Any questions? Yeah.
Thank you very much for the nice talk. Very interesting to see the similarities between the perceived dissimilarities of sounds and the semantic distances. However, I assume this was all on a population average level, and I was wondering how high was the inter-individual variability you observed in the perceptual dissimilarities across different individuals? And do you find individuals that maybe also put more emphasis on phonetic or acoustic features? And how can you explain this?
Yeah, we haven't checked these inter-individual differences, but what I would like to emphasize is that, for example, in the framework that we are using for the last MEG study that I showed, we used cross-validation, leave one participant out cross-validation, so we wouldn't have strong results if our model representation statistics were not generalizable well across participants. But we haven't checked well inter-individual differences in this case. Thank you.
Thanks.
Yeah.
Thanks for the nice talks. Lots of cool
Thank
stuff. In the STG, you see, the biggest thing you see is just selective responses to speech. So you see a really strong response to speech, and then an intermediate response to non-speech vocalizations, and then a weaker response to everything else.
Yes.
And if you look at your MDS plot, that's like what it looks like. So I'm wondering how much of the response, the prediction accuracy of your model is just driven by a speech selective response. Yeah.
Well, in our analysis, what we did, this was a question that we got from reviewers, and we repeated the analysis by removing speech, and we got essentially the same results in terms of model comparison.
But is that because, like I said, you see a big response to speech, then a weaker response to non-speech vocals? In other words, is it just that there's still some speech selectivity?
I know. You're absolutely right. Yes, but well, one thing is that within the fMRI study there was continuous speech sounds, but there was no continuous speech in the perceived dissimilarity study, where we found essentially very similar results. But yes, fair point. Thank you.